Well, good afternoon, morning for those on the West Coast. Thank you for attending the SolidCAM iMachining webinar today. We really appreciate your attendance. My name is Steve Welch. I'm the National Sales Manager here at SolidCAM, and we're looking forward to showing you a unique strategy called iMachining today. So just a quick introduction for the rest of the members on the team here. We have Ken Merritt from SolidCAM. Ken, are you there?
I am. How's everybody doing today?
Also, Scott Neal, another one of our senior application engineers from SolidCAM.
Hi, guys.
Good deal. Man, a few words. We're super excited to have a rather new partner on the line with us today as well. I'd like to introduce Jeff Rossio and Dave Pichette from Harvey Performance Tools. And gentlemen, I'll throw it over to you to just give a quick introduction of yourself and your company.
Yep, sure. Thanks, Steve. So we are from Harvey Performance Company. As Steve said, that's the parent company of 3 different cutting tool brands, which you all may know. We have Harvey Tool, Helical Solutions, and Micro 100. Harvey Tools, primarily known for miniature cutting tools and specialty cutting tools. Helical is more focused on high performance, larger diameter end mills. That is actually what we'll be running today, is a Helical Solutions tool. And then Micro 100, primarily known for their turning tools. So that's a little bit about us, and then I'll pass it back to Steve to talk a little more about the part.
Sounds great. Thanks, Jeff. Appreciate that. No, and I mentioned it earlier, a little bit of a newer partnership, but I know Ken and Scott really did some in-depth testing of Jeff and Dave's tool set, and we're really excited about what we see, and we'll be using that tool in the actual live cut that we're doing today. So just a couple housekeeping items before we hop in. You should be seeing a split screen. Ken's got the SolidCAM InventorCAM fully integrated slide up right now. If you pull that down, and when we get to the actual live cut, you can expand that that part of the screen to see the full view of the live cut that we're going to be doing today. So we also have everybody on mute just to keep the background noise to a minimum. If you do have questions, though, please at any time feel free to type those into the questions pane of the GoToMeeting. We'll answer those as they come up. Definitely want to get you the answers to questions, any questions you might have. So regarding the agenda today, I'd like to give you just a quick bit of background on SolidCAM as an organization. Then we'll give you an overview of the part that we'll be working on today, talk a bit about iMachining, and then get to the good stuff, the actual live cut. And I want to stress, this is not a recorded presentation. This is an actual live cut that we'll be doing right in front of you. So, and then at the end of the presentation, we'll just throw it out to open question and answer. For those that might be interested, though, Ken, I think you're still teed up to do kind of a science of cutting angle or science of cutting engagement at the end of the presentation, correct?
Yes, sir.
Beautiful. Yeah. Just in the interest of time, and so we can get our message across, we tried to get to the live cut and wrap that portion of the presentation up in about 20 minutes. So without further ado, let me just to give you a quick background on SolidCAM as an organization. We're privately owned, have been involved in CAM software development, sales, and support since 1984. Started out life as a standalone CAM product, quickly found out that an integrated solution really provided a lot of benefits. Our product is now fully integrated into both SolidWorks and Autodesk Inventor, and the iMachining module itself is fully integrated into Siemens NX product. So we handle customers here in the US and Canada with a direct team. So Ken, Scott, and I, along with the rest of both technical support, post-processor development, the entire team is all employed by SolidCAM itself. We aren't dealing with resellers here in the States for our product. So iMachining is our flagship product. We support everything though from 2-axis up to 5-axis simultaneous milling. Kind of proud of the fact the owner got ahead of the curve and really put a lot of money into research and development 8 years ago to control live tooling or mill turn type machines. So we're fully capable of the most complex mill turn machines you can imagine, multi-turret, multi-spindle. Even recently now have rolled out control for Swiss screw machines. So that's in our toolbox as well. Really pride ourselves on picking up the phone with a live person anytime somebody has a technical question, and also providing bulletproof post processors. We're not big believers in shipping out a library post. Each post that we develop and deliver is based on what somebody has, not just, hey, here's one that worked for somebody else. We gather the information on a customer's specific machines, put together post processors custom for what those machines have as far as features and additions. So I think that's it. Ken, did I miss anything?
Not that I could see. I think you got it good. Got it covered good.
Beautiful. No, I guess at this point, Ken, could I throw it over to you and just give the folks on the line an overview of what we're going to be doing as far as the cut today?
Absolutely. You betcha. All right. Thanks, guys. Like Steve said, I'm Ken Merritt, and we're just going to kind of walk you through what you're going to see in iMachining. We want you to see a live cut. Now, I'll give you a heads up. We're kind of running up the upper edge of the envelope here today. So you're going to see some pretty fast cutting. We also work with you to help you understand how to use iMachining very, very effectively in the production world, where we'll find that balance between cycle time efficiency and tool life as it fits your budgets better. So we work with you on that. Today we're going to show you some pretty serious cutting. iMachining gives us the ability to control the cut very simply. iMachining takes advantage of the tool characteristics, the machine kinematics, and the material properties. And by marrying all those together in a very special and patented way, we can give you this machining level slider to allow you to go from very, very conservative cuts down here all the way up to extremely aggressive cuts, okay, without having to figure out what all the numbers mean, okay? And we'll kind of take you through that. This is the part we're going to be cutting today. We're going to cut the pocket shown there with the tool path in it. The material is cold roll steel. It's about a 3.5 by 2 inch part. And we're going to be using one of Helical's HSV series tools, a 4-flute carbide high efficiency end mill. And we can get you some more information on those. Actually quite impressed with the tool. It runs really nice in here. So there's a little bit of information here about our partners. Helical, of course, is, as you said, a part of the Harvey Performance Company. And this is the tool we'll be using today. We're also holding that in a RegoFix power grip holder, which we can talk about later as well. Gives us fantastic holding power and true run out very, very well. Real nice piece of equipment. So without any further ado, Scotty, if you're ready to roll.
Hey Ken, before we do that, could you just maybe describe the machine we're cutting on? Because it always amazes me that the machine that we're utilizing in the live cut today. Could you just talk about that for a second?
Oh, certainly. In fact, give me just a moment. I had not thought about that. Let me pull that up and I'll show what we're using.
Yeah, and the only reason I bring it up for the audience today is that sometimes there's a misconception that, oh boy, you have to have a brand new state-of-the-art 25,000 RPM spindle to get the benefit of solid or iMachining. And boy, nothing could be further from the truth. We're cutting this on, well, Ken, it looks like you found it, so I'll throw it over to you. Okay, beautiful.
This is actually a 1996 Defiance CNC tabletop machine. We found this from one of our customers, had it in the back room with a tarp over it, hadn't touched it in years. It had an old DOS computer on it. And we grabbed it and we did a little retrofit on it, put some new servos, a new controller. You see the mock motion controller on there. and we dropped a HSD wood router spindle in here. It's a 3 horsepower wood router spindle, but gives us 18,000 RPM. This machine was really only ever designed to cut wood, plastic, maybe a little bit of light brass or aluminum, something like that. But that was pretty much the max. You can see it's sitting on a Lista cabinet, and so this is kind of the low end, if you will, of machine performance. Now again, we've done a little bit of retrofit on it, but it's still a little bitty guy. So I think you'd be impressed with what you see here. So this is looking inside the machine, and this is a 3/16 inch diameter tool. Scott, tell us a little bit about the stick out on that. What do you got that thing set for?
Okay, the tool's 3/16 diameter. We have 5/8 cut length on it, and we're sticking out from the holder, I think, right around 900 thousandths.
Okay, so pretty heavy diameter to length ratios here. What most people would consider on a tool this size to be a little bit tentative for doing any kind of aggressive type cutting. So we'll let you see what we're going to do. Again, this is a 4-flute tool. Nose radiuses are, I think, around 10 thousandths. And we're just going to go helix right into this block. We're going to cut it a 1/2 inch deep. So just over 2.5 times diameter depth of cut. And Scott, whenever you're ready, let's let her rock and roll.
Okay.
I'm gonna throw one more reminder too, because I was looking at just that small screen. You can expand or slide the screen on your GoToMeeting so you can view the full live cut as it's happening. So
Absolutely.
good.
All right. Let's see. You got everything at 100%. All right, and hit the green button.
All right, now we're going to be helixing in very aggressive as well. We're doing 15,000 RPM, 130 inches a minute at 1.6 degrees helical ramp angle. And now we're going to spin her up to 18,000 RPM, and we're running about between 180 and 220 inches a minute in this cut. And as you can see, we're 1/2 inch deep, moving very, very aggressively around this. And Scott, what is our spindle load looking at?
I'm looking at about 60% spindle load on this right now.
Okay, now that's 60% on a 3 horsepower wood router spindle that, when running in the air at 18,000 RPMs, takes 24% spindle load. So that's a very, very minimal load on this tool. And as you can see, beautiful surface finish in there, real nice, easy cut. Scott's going to show us a few of those chips that come out of there. Extremely constant chip thickness. This is what iMachining is all about. And notice also, tool's not hot, part is not hot, and this is because of the way that we are doing the cut, because of how we're managing the cutting angle engagement. All of the heat's coming off in the chip, okay? And so it makes it a very effective way of machining with minimal forces on your material, minimal forces on your tool, and minimal forces on the machine itself. And so you can see very effective productivity.
And by the way, Ken, that was a 54-second cycle on that.
54-second cycle, and that's, like I said, that's a 2-inch wide part. That's 3.5 inches long, 2 inches wide. So that gives you an idea what the size of that pocket is. We're probably looking around 1/750, 1/625 thereabouts on the length of that pocket. It's about 1 inch wide, and we cut that whole thing out of 1018 cold roll stainless steel with a 3/16 inch diameter tool in well under a minute.
And I think, man, I was really impressed by the sound of that cut too.
Absolutely. It sounds beautiful. It's a very different sound than what people are used to hearing, because it's much higher pitched because of the RPM. And it's the thing that is amazing to most people is how stable it sounds. You're not hearing loading and unloading of the tool. And we'll get into a little bit of that as we get into the idea of the science of cutting angle.
Nope. Super impressive. Ken, could you just speak? I know we just did a straight 2D cut, but iMachining is also available in full 3D as well. Could you just
Absolutely.
maybe, talk about that?
Yeah,
there we go.
Thanks.
Thanks, guys.
Yeah. What this is, the way we do 3D iMachining, and this is what really makes it super powerful, is while we are doing the roughing, when we encounter slope surfaces, as we're roughing, we automatically start stepping up those slopes so that at the same time that we're roughing, we're also creating that beautiful semi-finish that you see there and not really having a very negative impact on cycle time, because the semi-finishing is actually being done at the same time that we're doing the roughing. So this actually can obsolete the entire need for a final or a semi-final finish cut to get it ready for the ball tool to do the finishing work. You can literally go directly from a rough cut straight into a finishing cut and not encounter any kind of waveform in your surface. It really is pretty amazing the way it works. What we've seen, now this is I believe a 5/1000 scallop height. If you look at those stair casings in there, you can kind of see them. And so this is prepared for the finish, but we ran a difference between this part at like 40/1000 of scallop step and 5/1000 of scallop step. And we only picked up, this is like a 5-minute cycle time to do this entire mold core here. And we only picked up just like 20, 30 seconds max when we went down to that 5/1000 scallop. So that changes the game completely.
And this particular material is 17.4 stainless steel.
Yes, it is. Absolutely. And it's kind of amazing. Sometimes you'd be surprised. We cut 17.4 stainless steel, even though it's a pH hardening, precipitation hardening steel. We cut it dry as well with just the air blast on it, because and we can get away with that because of how we manage the engagement of the tool. Again, all that heat's coming off in the chip, and we're not imparting any of that heat into the part, so we don't cause that precipitation hardening that you see sometimes in traditional tool paths.
Excellent, Ken. No, and I'd maybe like to throw it over to Jeff and David at Harvey. This is an awesome tool, obviously, but iMachining doesn't require a super specialized tool to get these types of results. Jeff, could you just quickly again maybe describe the tool that we use today, if you could?
Yeah, so this is Dave. That's one of our HSV4s. It's a 4-flute end mill, variable pitch, so that you can kind of reduce the harmonics that you can sometimes combat when you're running the tool. It's got our A+ coating on it, which is great for steels, like the 1018 that we're machining today. And we iterated it earlier, but it's a 3/16 diameter with a 5/8 length of cut.
Beautiful.
10th corner.
Yep. Outstanding. One thing I've always wished we could incorporate into these presentations is to get a loop on that tool. But Scott, I think to your eye, the tool looks literally almost brand new, correct?
Absolutely. It looks like it just got it out of the package.
Sweet. Good deal.
Yeah, we have found, doing trade shows and such, we've found that we get just phenomenal tool life, even at these extremely aggressive rates. Now, obviously, if you're in a production environment and you're looking at tool cost per part and such, depending on where the balance is between your cycle time and your cost per part, you may want to back off. But that's the beauty of iMachining. We're running this at level 8 on the actual iMachining cut. You could back off to level 6 or level 5 and wind up making your tool last a little bit longer. We have seen, just as an example, doing these types of cuts, very similar to what you're seeing here at a trade show, every 5 to 10 minutes, maybe 20 minutes maximum between cuts, doing them all day long, and actually wind up getting a day and a half, maybe even sometimes a little bit more than that out of a tool. So the tool wear is just fantastic. One of the things that Scott and I were talking about yesterday, noticing with this helical tool, is that the cutting edge of the flute was very, very stable. We didn't see any microchipping on it. We didn't see any abrasion of the coating. So very well done, guys.
Outstanding. Good deal.
Thank you.
I think we'll throw it up to our open question and answer at this point, and I'll do a couple quick wrap-up things. But if anybody does have any questions, again, please feel free to type those into the questions pane, the flyout window in GoToMeeting, and we'll get those addressed. As far as a wrap up, and I do want to remind everybody, Ken is going to get into a presentation on the science of cutting angle and why this technology works right after I wrap up here and we handle the questions. So if anybody's interested in staying for that, please feel free. It gets into you know, some real good detail about what we're doing and how we're doing it. So just want to mention again that iMachining is SolidCAM's flagship product, but by no means all we are. We're not a one-trick pony. I mentioned it earlier. We handle everything in the milling aspect, from 2D to full 5-axis simultaneous. Live tooling support is there, and super excited about the ability to control Swiss screw machines. So if it's on your floor, we feel like we can control it really well. If you would like a private overview of SolidCAM, welcome a chance to get some part files from anybody that would like to send them to us, and we can concentrate on that and give you the full picture of what our software is capable of. So you can contact us at solidcam.com or 866-975-1115, extension 1, I believe, is our general sales line. So Jeff and Dave, I'll maybe throw it over to you guys too for a quick wrap up.
Yeah, sure. So if anybody's looking to, you know, learn more about a Harvey Performance Company in general, any of our brands, you can head over to harveyperformance.com. And if you're interested in this helical tool specifically, you can come check it out. It's www.helicaltool.com, or you can give us a call at 866-543-5422 and talk to one of our tech team members about how we can help you out.
Outstanding. Thank you.
Hey, Steve, I see a couple questions
Yep.
in here. One question is, do you need a high RPM spindle for this? And I'm going to actually get into that a little bit in the science of cutting angle. What iMachining is going to do is take whatever you've got for a machine and make it perform significantly better than you've ever seen it perform before. If you have high RPM spindle, then of course you can take advantage of the higher surface footage on the tool. If you don't, we're still going to use the maximum of what that machine can do when it's appropriate to do that, and we're going to optimize that performance for that machine. I'll show you a video that gives you a really good example of that. The other question was, he says, right now, working with HSR and HSM milling in 3D implants, can I also implement iMachining here? We work with STL files. STL files are a little bit more difficult to get into. If you can convert the STL file into a what they call a dumb solid body, a watertight manifold solid body, then we could apply the iMachining 3D to that. We have not yet taken iMachining 3D to the level of being able to handle the STLs. That probably will be a future enhancement, but I couldn't tell you exactly when.
Good deal. Anything else, Ken, coming in on the questions?
You know, I don't think so. I think I see no more questions in there. So I guess at this point, we probably ought to jump right into the science of cutting angle. And if you'd like to stick around, this is a kind of a science dissertation on what you just saw and how that worked. So perfect.
Sounds good. For those that have to leave, we thank you for the time, and for those who stay, we look forward to giving you an overview of the science behind this.
All righty. Okay, well, let me just do this. I want to take us into the PowerPoint again. Now, this is actually that video that I was talking about. Let me explain a little bit about this as it starts running, and we'll talk about what's going on here. Now, this is a very old, and I do mean very old, Haas TM2 open bed tool room machine that one of our customers had up in Denver. And we were looking at it. He was cutting pockets very similar to this shape, and he's using a fairly decent tool in here. It was not a super high-end tool, but not a junk tool either. But he was only able to get 50,000 step down, 2,200 RPM, 18 inches a minute on this machine was the best he could do. It's 3/8 inch diameter, 3-flute tool. And that was you know, the machine was rattling so bad that if he went anything greater than that in performance, it started to chip the tool up. It's because the machine's not sturdy enough. It's, you know, it's kind of rickety. So this pocket took him 2 hours and 26 minutes to cut. And at the end of that cut, the bottom 50 thousandths of the tool was completely gone. This is a 1-inch deep pocket. Now, as you notice with iMachining, I've taken it all the way down to the full depth of cut, full 1-inch deep on a 3/8 tool, okay? Now, this is only a 4,500 RPM spindle, and the machine can only do about 50 inches a minute before it starts getting into data saturation and starts hesitating. So we can't really do a high performance cut like we did just now today for you guys. But I want you to think about what we're doing here. And remember, this was 2 hours and 26 minutes. So let's go ahead and take this video up towards the end of it here so you can kind of see what it did. Look at the chip color. You know, we've got most of this thing cut out now. Again, it's not a real sexy video. It's not high performance. It's not moving real fast. But I think you're going to be amazed about something here. We're done with the pocket right here. Look at the color of the chip right here. This was a 7-minute and 26-second cycle time. Now, what blew this guy's mind was we pulled this tool out and looked at it under a 3x magnifier, and you couldn't tell it was a used tool. I mean, we wiped it down with MEK, obviously, and blew it all off. It looked like it came right out of the box. There wasn't even any scuffing on the coating, okay? This particular tool had chamfers on the corners instead of nose radiuses, and even the 2 corners of the chamfer, the coating wasn't even starting to discolor yet. So we put it back in. We cut 3 more pockets on this bar. At the end of the 4th pocket, remember, each one of those was 7 minutes and 26 seconds, not 2 hours and 26 minutes. At the end of the 4th one, we pulled the tool out again and looked at it under the scope, and you could barely tell it was used. There was a shine mark right down the sharp edge of the flute where the coating had been kind of abraded away, maybe 3 to 5 thousandths away from the sharp edge. The tool was still razor sharp. The corners on the end, on the nose corners, were just starting to turn color. And in the ejection galley, you could see a little bit of scuffing on the coating. So I'm going to guess we probably could have at least got another 4 pockets out of it, possibly even 10 to 12 pockets out of it before that tool became really unusable. He was getting 1 per tool, and it was taking him 2 hours, 26 minutes to cut the pocket. We did it in 7 minutes, 26 seconds. So huge, significant improvement, even on the performance of an older, low performance type machine that was not designed for high speed machining, okay? Now, as we look through this, if you have a machine that you can take advantage of high performance, then of course you're going to get some better performance. I like to use these 2 videos to show you a little something. We did some crazy tool designs and we're testing this tool, but this video is in a milling chuck, okay? This is not an ER collet, but this is one of the double angle chucks. And you can see we're getting some pretty aggressive cutting here. This is a 12 millimeter tool. We're cutting at 14, or at in this case, we're 12,000 RPM, 350 inches a minute at 55 degrees cutting angle. Okay, pretty aggressive, nice little cut. But I want you to see something that happens here, and this is one of the things why we promote the RegoFix holders and some of the other high-end holders in the market today. Because as you see this thing go around this corner back here, look at what just happened right there. Okay. This holder, even though it's a reasonable, it's not one of the best ones on the market, but it's not one of the worst ones either. Even though it's designed around holding that tool really tight, and it's got, you know, special clamping angles and everything, at this level of performance, it was not able to hold the tool. The tool started pulling out, okay? Depending on in fact, this tool had a 50-degree helical angle, so that's a lot of downforce, okay? Maybe you shouldn't even expect a holder to hold like that, okay? But we put it in the RegoFix holder, same tool, same material, same depth of cut, except this time I'm running 14,000 RPM, 512 inches a minute at the same 50 degrees cutting angle, 55 degrees cutting angle. And notice that we don't have any problem with pullout. And that's because when you're using the right holder, and especially for instance, these RegoFix holders, they actually even have more holding force than the shrink fit holders. And they're just absolutely true run out. And so this is kind of a unique video. Again, I was pushing this tool to its limit to try to see what it could do. And iMachining did a great job of managing it. You can see how much material has come off of that already. Let me go ahead and ramp this forward for you a little bit and show you what we got to when we get down to the end of this. Now this is a 5x3 block of steel, and we took it down to those two shapes in 1 minute and 27 seconds. So the performance of the machine, the performance of the tool is going to allow iMachining to take it to a higher level. But in answer to your question, do you need a high RPM spindle for this? Not necessarily. We're going to increase your productivity through whatever machine you've got, okay? Now, as we go on into this, let's start talking about why this works. Let's see what we're talking about here. We're looking at the science of cutting angle, which is a little bit different than tool step over. We're looking at how the tool is engaged in the material and how does the software control that engagement. One of the things that we need to be aware of, we always talk about cutting steel, okay? We're not really cutting steel. This is kind of a unique and interesting video. This is a lathe insert with a, I believe this is a 1/1000 or a 2/1000 nose radius, maybe 1.5. But you can see what it's doing here. This is actually going through similar material to what we cut today, a cold rolled steel. I don't know if it's 1020, 1040, or 1018, but you can see underneath here, you can see it actually, the material actually kind of bending. Let me start that again and let you run. You can kind of see it bend and come back up. That's known as elastic deformation. But along this transitional line here, you're seeing what's called plastic deformation. This is actually a disheveling or a chiseling, if you will, of the molecular structure of the material. And this is the chip formation. This is how it works, okay? Now, one of the most important things is the cutting edge velocity and its relationship to the chip thickness. Now, as we look at this diagram, we have a rotational velocity on the flute, okay? And we have a forward velocity on the tool. When that is in balance with proper cutting angle, the pressure vector is over here in this range, nearly tangent, very, very close to being tangent to the curve of this flute as it engages the material. And why is that important? Well, carbide is extremely hard, and it can stand up to a lot of pressure. It can't stand up to tensile force because it's also very brittle, okay? And so anytime we create a tensile force on the flute itself, we're going to stand that chance of microchipping or actually fracturing the carbide substrate. If we can keep that pressure vector in a near tangent alignment to this flute all the way through the cut, then that flute is seeing pure compressive force. And it's designed, carbide is designed to handle compressive force, and it handles it very, very well. Now, an illustration I like to use is a sharp knife on a tomato. If you take a sharp knife on a tomato and you push straight down on it, you will chop the tomato, but you'll also squish the tomato as you're doing it, right? But if you take that same knife and you drag it very fast across the tomato, it'll virtually slice through it without any deformation whatsoever, okay? Now, the physics of this are not exactly the same as what we're talking about, but the illustration works very well. As we increase the cutting edge velocity, we decrease what I like to call the latent energy of plastic deformation, okay? Now, there's a lot of different things that happen with that, and one of the things is that it allows us to carry a heavier chip. The heavier chip means we can take out more heat. Because as we increase our velocity on the cutting edge, we're going to increase friction, we're going to increase thermal dynamic. And so we need to get rid of that thermal. And allowing us to carry a heavier chip allows us to get that heat out of there, which means we can increase the velocity, which means we can increase the chip thickness, and so on and so forth. Now, there is a limit to that, of course. But you saw us today in a very, very aggressive cut. That was 884 surface foot at a 2/1000 chip thickness, not a chip load at the front of the tool, but a chip thickness. We'll talk about that in a little bit. The stability of that pressure vector is also extremely critical to the flute integrity, okay? If this pressure vector starts to swing, then we're inducing vibration into the tool substrate. And again, carbide is great at compressive force. It can't handle shock, okay? Whether that's thermal shock, whether it's impact shock, or whether it's vibrational shock, that will tear down the carbide substrate and reduce the life of your tool. In a traditional style of tool path, there's several things that happen that are very detrimental to the tool and to the material. We want to talk about those for just a short second. Most traditional tool paths are kind of like a racetrack profile here, like you're seeing. At each one of these locations where the tool has to change direction radically, we end up in what we call a compression zone, and the tool goes into a full slot mode cutting. Now that has a couple of very bad things happening to it. Number one, on the left side of the tool, in the conventional cut mode, we have chip thickening going on, which means as the flute progresses towards the front, it's going to see an increase in the latent energy of plastic deformation because the chip thickness is growing, right? On the right-hand side, we're in a chip thinning functionality. And so the plastic deformation, latent energy of plastic deformation is going down as the flute travels and progresses through the cut. Something else that's happening over here on the left-hand side, the chip that is trying to get evacuated is actually being pushed directly into where the tool is moving. And that creates a condition known as chip compaction, okay? So as we think about that, we think about the progression of that tool pressure vector. As it begins into the cut in this slot style cut, that pressure vector is virtually directly opposite the direction that the tool is traveling. It creates a linear or a bending force on that tool, which is that tensile force that we don't want that tool to ever see, okay? As it progresses up to the thickest point of the chip, the greatest pressure against it, the tool pressure vector is basically 90 degrees to the travel, which is why it causes it to flex off of this wall, and we always have to come back and do a skin cut back here, okay? So a lot of things going on here that really create a problem. That chip compaction adds to that linear force vector, and it also, because of the chip compaction, we get conductive heat transfer into the part, into the tool. And that's where we wind up burning tools up if we try to get up into too high of a surface footage velocity. Okay, now, the worst thing that happens in this situation is pressure vector oscillation. Right here at this front end of the tool, as it relates to the direction it's moving. As the tool crosses the 90-degree quadrant, it's just an instantaneous moment in time. But at that moment in time, when it crosses that 90-degree quadrant, the effective rotational velocity as it applies in this ratio of forward velocity to rotational velocity becomes 0 for an instant in time. Problem is, you still have forward velocity on the tool. And so that causes the pressure vector to flip to the outside of the flute, and now you're seeing pure tensile force for just an instant of time, creating that harmonic vibration, okay? Now, one of the things that Dave talked about earlier with their tools is that variable pitch and variable indexed flute that helps to dissipate harmonics, okay? Well, iMachining helps even more by not taking you into that zone of the cut where those harmonics are generated radically, okay? We do that by limiting the maximum cutting angle to 80 degrees, so we never cross the quadrant and we never see that vector flip. Okay, why 80 degrees? Well, we did some practical studies, and somewhere between 85 and 90, depending on the ratio of rotational velocity to forward velocity, we began to see an increase in harmonic vibration, indicating that that pressure vector was beginning to sweep. Okay, below 80 degrees, it really stays pretty stable. It's amazing how low the vibration is on these cuts. 10 degrees minimum helps keep us from burnishing the tool, and anything below 10 degrees really not taking any material off, so your volumetric removal rate becomes pretty wimpy, okay? Now, let's go back to a traditional pocket for a moment, just to look at it again. Racetrack style profiling, okay? Every single one of these corners is going to create a problem for the tool. and for your machine as well as for your material. You're creating work hardening, you're creating work-induced stresses, you're doing all kinds of different things to it when you move this type of a file. Limited cut depth, because as our axial cut depth goes up, the forces, those linear forces on the tool, go up on an order of magnitude. That's why we traditionally don't see more than about 1/4 of a radius up to about 1/2 a radius depth of cut for a traditional pocket. Because anything above that, we start snapping the tool off. There's just too much pressure on it, okay? We did for years, we did standard trochoidal, which, you know, we orbited into the corners, and it helped. It wasn't really the right thing to do, but it was better than this one. What did we do? Well, iMachining, SolidCAM decided to rewrite the motion algorithm. We rethought how it was going to be done, and we used what's called a morphing spiral. Okay, so let's talk about this toolpath for a minute. This is the D-slot trochoidal mode of the morphing spiral, but basically this is the center of the tool. We follow it down here. It helixes up off the floor. Default value is 3,000, but it's user adjustable. It does a high feed G1 move to here, helixes back in and takes the next cut. Helixes off, high feed reposition, helixes back in, takes the next cut. There's never, ever a sharp corner in this toolpath. There is nowhere for that tool to overload. We can manage that cutting angle very effectively by managing the next step in the cut to change its vector direction to keep it within the cutting angle parameters that have been assigned. The morphing spiral aspect of it is really cool. When a morphing spiral is done correctly, there is no more efficient way to remove material because you're not repositioning. You're keeping the tool in the cut. That's also better for tool life, and it's better for machine life, okay? So how do we accomplish that in a shape like this? Well, one of the ways we can do it is we use a separation channel using the D-slot trochoidal style that we talked about here to clear a path around this so that we can spiral morph this from the outside to the inside where we would never run into an internal corner again. Makes it much easier to manage that cutting angle. This looks a little bizarre right here. What this is if we took this channel width all the way out this side or this end, we'd wind up leaving a thin wall standing right here, and we'd have to come back and take care of that. Now, because we're using extended axial depth of cut, today we were at just over 2.5 times diameter in depth of cut, but we have actually gone, I personally have gone up to 5 times diameter depth of cut without any problems at all, okay? If we were doing that with a very thin wall right here, we stand a chance, depending on the malleability of that material, of pulling that material over into the tool, which of course would cause tool breakage, okay? So the idea here is with the thin wall thickness variable that we put into the system, if the algorithm sees that this channel width would violate that thin wall thickness, it simply expands the channel, takes that out on the way, so we don't have to deal with it. Okay? A little bit of a different view, isn't it? Now, a lot of people ask, well, isn't this a lot less toolpath? I mean, look at all the lines here versus what's here. You would think that, except that remember, this is an inch-deep pocket. On a 1/4 inch tool, we can do that in one cut. Inch-deep pocket on a 1/4 inch tool here, we're going to take in 50,000 step downs. So we're going to take 20 passes of this and significantly slower speed and feed than what we're doing this over here. So believe it or not, this is a far more efficient toolpath, and it's amazing how much more efficient it is than doing this. And you get better tool life and everything with it. Now, I said the morphing spiral is the most effective way of removing material if it is done correctly. Let me talk about that just for a brief moment, and then we'll move on. If on a long, narrow area like this, I were to take a channel across here and separate this area from the wall so the tool can move around it, in order to collapse to a central collapse point across the narrow side at the same time we do across the long side, across these short sides here, we'd be at the maximum cutting angle, or very near the maximum. But along these long sides, we'd be at or very near the minimum cutting angle, where we wouldn't be doing that much work, okay? Again, we'd cut very effectively across the short side, but then coming back across this long side, we wouldn't be doing much at all. We'd be barely fuzzing skin off of it, okay? So we looked at it and we built what we call spiral efficiency separation channels. The algorithm automatically analyzes the topology of the area, splits it into more symmetric regions where we can keep the tool in the spiral morph closer to or at the maximum cutting angle so that we get the greatest efficiency possible in that morphing spiral. So this is something that the system does automatically for you. You don't ever have to think about it. We also support rest machining. So if you want to use a larger tool to cut this area out, we can come back in and find those areas where we didn't cut, pull those out with a smaller tool. We also do a function we call iFinish. Now, this is interesting, okay? This even caught me off guard 10 years ago when we first started thinking about it. I hadn't thought about this until that time. Now it just makes all the sense in the world. If this model radius is very near the radius of the tool, then even if we've only got 10,000 stock on the wall, as you come into this corner, you can actually over-engage the tool. And you wind up, what did we talk about happens when it over-engages? You get a pressure vector that pushes linear force against the tool and causes that tool to flex away from the material. Okay, well, there's only 10 thousandths of stock, so when it flexes away just a little bit, suddenly it pops out of the cut, all those forces go away, and bang, it snaps back right into the wall. Generally, it overflexes a little bit, keyhole cuts the wall, and then pushes itself back out again, and you get this chirp, 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 chirp through the corner, and it leaves those nasty diagonal lines in there and makes a little keyhole cut for you and ruins your corner. That's because it's actually being overloaded, even only with 10 thousandths of stock. Depends on how near the radiuses are to each other. What iMachining does automatically is it looks for those over engagements, uses our D-slot torcoidal morphing spiral to go in there and clean those corners out down to the minimum cutting angle, so that when we come through with the finished cut, we're not going to burnish the tool, but we're not going to overload it either. And so we get a nice, clean, beautiful finished cut through here on our finished cut without worrying about any of that chirp and chatter. As Steve was saying, if you have any questions whatsoever, we'd love to talk to you. We'd love to give you a personalized demonstration on the software. Not a high pressure sales organization. Come talk to us. We'll help you out. If you're interested, we'll work with you. If you're not, we'll leave you alone. But check us out on the web. And one of the things you can do here is there's also, it's not shown in this picture, but at the top of the web page, there's a star that is our reviews. If you click on that and go inside there, you'll see we're close to 300 reviews already. We've only been doing this for several months now. And we're holding, Steve, what is it, about a 4.92 out of 5, I think right now?
I think it is, and yeah, yep.
So pretty good reviews. Go ahead and read those, and you'll see what our customers are saying about us.
Outstanding, Ken. No, thanks for the presentation. A lot of information, but all good for sure. So I'll throw it out one more time for any questions before we wrap up. Doesn't look like anything new, Ken. So
let me take them through just a brief look at the dialogue so they know what it looks like.
Okay.
This is, again, how easy it is to program iMachining. We have a dashboard that allows you to put all the pertinent information on one page, or if you want to go in deeper, you can go down, you can do the geometry selection based on feature recognition or based on typical profiles. You can select your tool here from our tool table, set your levels. These green colors indicate that the wall that I picked here and down at the floor is now associative. So if this model changes in SolidWorks, because these are associated to those pick points, those values will change automatically, and you get an automatic update of the toolpath with an engineering change order. Then we get to the technology wizard, and this is where it's cool. This is the angle that I was talking about, okay? And notice at level 8, we're really aggressive, but as we start ramping it down here, we become very, very conservative, very thin, lower heat, lower spindle speeds. Notice we're only at 3,900 here. But as we begin to ramp it up, it gets thicker and thicker in the cut. We get all the way up to level 8. We're running 18,000 RPM, 204 inches a minute at the full cutting angle. Now, view 2 allows us to see the velocity, the chip thickness, which is the chip thickness is at this cutting angle. It's not out here at the front of the tool. That's a very, very important thing, because one of the reasons that we stay very, very stable in our cut is because we also manage our feed rate as those angles change between minimum and maximum. We're managing the feed rate to make sure that we maintain a very stable and constant chip thickness. And that way the load on the tool is very consistent. Numbers that we were looking at today, we were up to, Scott, I think you said 60%, 57, 60% on spindle load.
Yeah,
And
around
that,
60, 61% on
60,
with the max spindle load, yes.
Right. And that's on a little bitty tool. But remember, it takes 24% spindle load to spin that tool at 18,000 RPM in the air. Okay, so we're looking at a 37% or thereabouts maximum spindle load delta from idle or from free wheeling. So very, very low spindle forces due to the way that we're managing that cutting angle and managing that constant chip thickness. And one of the things, you don't see that spindle load varying a whole lot either. So it's pretty cool. Technology page allows you to put in a couple variables like island and wall offsets and things of that nature. You can also notice that we've got our technology in here. You can do roughing only. You can do roughing and finishing like we're doing here. You can add in various control features for that finish pass. You can set your links up and away you go. So pretty easy to work with. Again, you don't have to do a whole lot of thinking with iMachining, because we take care of the machine kinematics, we take care of the properties of the material, and we take care of the tool characteristics to marry them all in a way that makes total sense for doing a scientific cut.
Good deal, Mr. Merritt.
So it looks like there is another question too.
Aha.
Scott.
Are you planning to integrate helical tool STL models into SolidCAM tool table? That'd be a great question for Dave. And yes, we are. Dave and Jeff and I have been talking about that already.
Yep. So it is a good question, and it is something we're definitely looking to do as part of this new partnership. We're going to get, updated Helical and Harvey tool as well. We'll be working on both of those brands, and then down the line, Micro 100, once we get some more, data and integrate them into the company. That's a new acquisition, so that'll take a little more time. But yeah, definitely both Helical and Harvey tool. The goal is to get tool models into SolidCAM for all the SolidCAM users out there.
Thanks, sir. All right, so if there's any other questions, please pop them in there right away. If not, we really thank you for joining us today. We know your time is valuable, and so we want to try to keep this under an hour, and looks like we're going to succeed today.
All good. All right, looks like no final questions, Ken, so with that said, I'll thank everybody for the time as well. Have a good rest of your day, and if SolidCAM or the folks at Harvey Performance can help in any way, we'd welcome the opportunity. Thank you all.
Thank you, everybody. Have a great day.
Thanks, everyone.
Bye now.